Let us check the continuity of this function to fx equal to 2x plus 3 at x equal to 1. So you just have to do certain things. This function is defined at x equal to 1. You see 2 into 1 plus 3. It is defined. Means if I would have placed 2x plus 3 by x. So this is not defined at x equal to 0 because we cannot have 0 in the denominator. But x equal to 1 it is defined. The value is 5. So let us find the limit of the function at x equal to 1. Limit x tends to 10, x tends to 1 at this point is 2 into 1 plus 3, that is 5. So the 5 is nothing but the value of function at 1. Both are 5. So f is continuous at x equal to 1. Examine for fx equal to x square. This is continuous at x equal to 0. Okay. First of all, it has to be defined. If you place 0, then the function does not become infinite or indeterminate. So it is defined at x equal to 0 and the value is 0. Let us find the limit. The limit is x tends to 0 fx. Let us place the limit, that is 0 square, that is 0. So the value at x equal to 0 and the limit at x equal to 0, they both are same. So the function is continuous at x equal to 0. Fx equal to mod x at x equal to 0. So mod x is, if x is less than 0, it will be minus x. If x is greater than 0, it will be x. That is the modulus. So by definition, fx equal to minus x if x is less than 0. It is x if x is greater than or equal to 0. Let us apply. First of all, if you place 0 here, the mod of 0 will always be 0. Right? But if the left hand limit is taken and the right hand limit is taken, 0 minus means 0. Means minus x. So you have to place 0 here. So minus 0 is 0 only. Let us place 0 plus, that is plus 0. Plus 0, that is plus x, is 0 again. The limit is 0. The value at x equal to 0 is 0. Both are equal. So f is continuous at x equal to 0. Show that this function is not continuous at x equal to 0. Let us see. First of all, it is defined at x equal to 0. It is defined. It has a constant value which is 1. At x equal to 0, it is 1. We have to check at x equal to 0. When x is not equal to 0, the function is nothing but a polynomial. It is a polynomial. And I'll tell you after this completion of this discussion. If we apply the limit, place 0 here, it will be 3. And see, the value at x equal to 0 is 1. But the value of at x equal to 0, when we apply the limit, is 3. So the value of x equal to 0 does not coincide with the limit at f0. That is why this function is not continuous at x equal to 0. So please understand, all polynomial functions, they are continuous. So only this x equal to 0 is the point of discontinuity in this particular example. Next is, check the points where the function fx is equal to k is continuous. Check the points. The function is defined for all real number because the value will be k in any way. Let c be any real number. Let us apply the limit x to c. When we apply x to c, then also it will not change. It will be always k because fx is k. You put any value of x, it will give you k. So the value is k of the function and the limit is also k. Both are equal. Then the function is continuous at every real number. Prove that the identity function on real numbers given by fx equal to x is continuous at every real number. See, if you place c here, any real number, you get c. This is identity function. When you apply limit, that is x tends to c. If you apply x tends to c, that is x. Fx is x. This will be c. In both the case, these are c. So this function is continuous at every real number. Right? Now, let us have some extension to our definition. What does it say? A real function f is said to be continuous if it is continuous at every point in the domain of f. So the domain has to be there. Sine function is defined or is continuous. Well, it is continuous actually, but for a certain domain it is defined. Various functions which are not continuous, but for a certain range they may be continuous. For certain domain they may be continuous. So this we elaborate what we have just said. Suppose we have f as a function which is defined in a closed interval, means closed interval means a and b are inclusive. So it may be say 7 to 15. This may be a range. Here f is continuous. So if it is continuous at f, it needs to be continuous at every point in a and b, that is 7, 8, 9, 9.1, 9.3, 11.6. At every point between 7 to 15, the function has to be continuous between a and b and including a and b. So continuity of f at a means when you apply the limit a plus, what is ab? The left hand limit is a plus. The right hand will be this will be b minus, because in this range a plus will be the limit and b minus will be the limit. So when you apply a plus, because this is the range, it will give you fa. You put a here. If you apply b, you get fb. You just observe that this extends to a plus and extends to b plus fx. It does not make sense. So if this doesn't make any sense actually, because of this definition, f is defined only at one point. It is continuous there. That is, if the domain of f is singleton, means if you have a singleton, f is a continuous function. If the function defined as fx equal to mod x, is it continuous function? See, x means if x is less than 0, it will be minus x. If x is greater than 0, it will be plus x. So let us rewrite in a function form. Fx equal to minus x if x is less than 0, that is in the number line, this portion it will be minus x, this portion it will be x if x is greater than or equal to 0. And we know that f is actually continuous at x equal to 0. You have just seen in the example. Let c be any real number such that c is less than 0. Let us assume one more c which is greater than 0. In both cases what happens? If then fc is nothing but minus c. So when you apply a limit x tends to c, it will be minus x. That is minus c. How about applying for c greater than 0? The fc will be c if you take this function. If you apply c here, it will be minus c. If you apply c here, it will be plus c in the case of x greater than or equal to 0. So we have taken the value greater than 0. So fc will be c, not minus c, because we are talking about this part of the number line. So x tends to c. If you place c, it will be c, unlike the case here. So we see that since the function fx, the x to c is equal to fc, that is, you are getting c, and at x equal to 0, you are again getting the equal number. So it is not valid for negative numbers. You are sorry, this one. This is correct. This is not correct. Not correct means it is not defined here. So f is only continuous for positive real numbers. For this number, because if you apply x as c, you get c. And when you apply x equal to x to any function, this function, it will be, if it is greater than 0, then it will be c. Both the cases, c will be equal to c. But here there is a problem. So we say it will be only valid for positive real number. So f is continuous at these points. F is continuous at all positive real numbers. Discuss the continuity of this function. This is a polynomial function. So f is clearly defined, right, for every real number. Say we take c. So if we place c here, it will be c cube plus c square minus 1. So we know that this, if you apply x tends to c, this will be c cube plus c square minus 1. So limit also says it will be this. If you apply c directly to fx, apply c, you get this. These two are exactly equal. So the limit x tends to c for fx is fc. So f is continuous at every real number, So now f is continuous function. In fact, every polynomial is a continuous function. Discuss the continuity of the function this. Fx equal to 1 by x. S should not be equal to 0. So if you apply c here, it will be c, 1 by c. When you apply the limit, it will be 1 by x, that is 1 by c. So the value of the function at c, the value of function at the limit of the function at c is 1 by c. So c, at every point you get the f as continuous, 1 by c, but c should not be equal to 0. So this is not defined for c or x. This is only defined for values which are not zeros. You cannot have a 0, but for others f is continuous function.